My name is Haizheng Zhong, and I come from Beijing Institute of Technology. And the title of my talk will be In-situ Fabricated Perovskite quantum dots from synthesis to applications. So this is the outline of my talk, and I would like to start from the basic knowledge of quantum dots, and then I would like to introduce the in-situ fabrication of perovskite quantum dots. After that, I will highlight the key points from my talk of in-situ fabrication of perovskite quantum dots. Finally, I will end with a summary and my perspective. So I think what are quantum dots? This is a basic questions, and actually they are quite small size nanocrystals. How small is it? We all know that the Earth, so it's like 6 million lies is soccer balls, and the crystals are like 6 million smaller than the soccer balls. So although they looks like a small crystal, but in details, they are capped by organic ligands. It's a hybrid materials. And if we can look into the more details, the inorganic cores were usually composed by the core shells. So this is the details, like what are quantum dots. So when the size of quantum dots are smaller, and when the size are comparable with their Bohr radius, they show very interesting quantum confined effects. Compared with the bulk materials, quantum dots show discrete energy states. So this is the most important features. So the quantum confined effects can be described by this well-known equation or Bohr's equation, and so because of the quantum confined effects, so with the size tuning, the optical properties can be varied by controlling the size. For example, for this calcium telluride nanocrystals, by varying the size from 1.8 nanometers to 6.6 nanometers, the absorption bond and also the PR emissions can be tuned from like blue to near infrared. In addition to that, quantum dots also show very interesting properties, such as multiple exon generation. In conventional bulk semiconductors, one photon only generates one electron hole pairs. While for quantum dots, they have potential to show to generate multiple exons, and this is a quite interesting phenomena, which helps for lasering, photo detection, and also solar cells. So in addition to the interesting phenomena, with the size decrease, quantum dots also show very important effects or in improved surface to volume ratios. Here I have a picture to show for well-known cadmium selenide quantum dots. With the size decreased to 5 nanometers, the surface atoms increased to 20%. And for 2 or 3 nanometers, the surface atoms increased to over 50. So with this increased surface atoms, they provide a good platform for functionality. For example, with this important surface, they can be combined with conductor molecules, proteins, and also other functional small molecules. And this, so how quantum dots was discovered? And it's really an accidental observation from a bare lab. And the most FAPbl people is Professor Louis Burrows from now from Chicago University, from Columbia University. He used to work in bare lab in 1980s. At that time, they reported the observation of side effects of the colloidal nanoparticles in liquid. So it's almost 40 years ago. So if you want to learn the history, I would like to recommend in 2040, Professor Angel Logash wrote a short paper titled with quantum dots still shining strong 30 years on. And in this paper, he described how quantum dots were discovered. And at that time in Soviet Union, and Alexander Alfres and Alex Klimov, and they investigated the quantum dots in their glasses. And at the same time, Louis Burrows from Columbia University, and they investigated the quantum dots in liquids. And actually, here I would like to mention, except for the well-known QDs in liquid, there are quantum dots doped glasses. So when quantum dots was discovered in 1980s. So here I would like to recommend a short review paper from ACS Nano, just published a month ago, which was written by Professor Alexander Alfres and Louis Burrows. And this review paper traces nanocrystal quantum dots research from the earlier discoveries to the present days into the future. And they describe how quantum dots was discovered and also the milestones during the developments. And this is a good paper to learn the histories, and I enjoyed it very much. But here I would like to say that this review paper doesn't tell us anything about the in-situ fabricated perovskite quantum dots in polymer matrix, and which bridge the quantum dots in liquid and in glasses. And this is also the key point of my talk. Hopefully, and my talk can supplement your knowledge on quantum dots. Okay, here I have an outline to describe the milestones of the development of quantum dots for applications. So after about 10 years of the development of quantum dots, so in 1993, Professor Bawendi from MIT, who reported the breakthrough of hot injection synthesis. After that, people start to investigate the application of quantum dots in different fields. So in 1994, Professor Olivisato, they investigated the use of quantum dots as emitters in light-emitting diodes. In 1998, Professor Olivisato and Professor Shuming Nie from Emory, and they report the use of quantum dots in bioimaging at the same time. So later on, there are different applications was reported, and for example, later in 2000, and solar cells in 2002, and the image sensors in 2005, and displays they were launched in 2012, and now they become a very large market. So according to the touch display research, there are at least 120 companies working on the commercialization of quantum dots, including Samsung, Apple's, BOE and TCR, and among them, several companies they were founded from the university. For example, Nanocrystal from Imperial College which was founded by Professor Owen. Nanosys from Berkeley and QD from MIT and Nanotech from ZDU by Professor Xiaogang Peng. And about 5 years ago, and Zhong was also founded, who develops perovskite quantum dots for the commercialization. Okay, I would like to briefly describe how synthesis of quantum dots, and there is many ways and describe how QD can be synthesized. Here I have a MOE from web page and describes the fabrication of conventional cadmium selenide QDs. Hopefully you can see the MOE. Okay. With the increase of temperature, there is a interesting color change from yellow to red, and with the increase. Okay. So here you can see that with the time per round, like the color changes and the spectral redshift with the size increase. Okay. So although there are different synthetic methods was reported, and there are many successful fabrication rules, I think Professor Ligands contributed a lot on the development of the hot injection synthesis for cadmium selenide and also different materials, in particular in shape control and also many like different things. But the fundamental things for the fabrication of semiconductor quantum dots from the viewpoint of thermodynamics is just the form of small sized particles with enlarged surface volume. And in comparing with the formation of other conventional bulk materials, the formation of quantum dots induced a new term of the surface formation energy in addition to this volume energy. And from the viewpoint of dynamics, the key point is the growth of small size particle is much faster than the larger size. And this makes the formation of QDs can be narrowed down to with the reaction prolonged. And this is quite important. And the most successful fabrications gives high quality quantum dots with size distribution less than 5%. Okay. Okay. So with the time per round, quantum dots, the family of quantum dots expand to different materials. At the beginning, maybe they firstly the 2,6 groups QDs were synthesized. Later on, people expanded to 4,6, such as lead sulfide and lead selenide. And also with the time per round and indium phosphide and indium arsenide was successfully fabricated. And there are also reports on the silicon quantum dots and copper indium sulfide, and very recently perovskites was developed. So almost most of the semiconductors can be achieved, and with a series of QDs. Okay, so for quantum dots, except for the family embedded expression, there are also size and shape control. Here I show some demos which was fabricated by myself in the past 2 years, and we can tell the size, and we can fabricate different like shapes and tetrapoles, which was firstly reported by Professor Mana, and there are also different like Y shape, different shapes. So for the composition control, composition control is a quite important strategy for bond engineering, and this is important in conventional fabrication of semiconductor thin films. And this strategy was also adapted for quantum dots in 2003, and Professor Wolfgang Thun from Germany, and they worked with Xinhua Zhong, and they reported the first composition tunable zinc cadmium selenide nanocrystals with the tunable emissions. And this is quite important because although we all know that by tuning the size, the PR emission can be varied, but in the real industrial applications, actually the color tunability was achieved by controlling the composition. So doping is another key point for semiconductors, because in bulk semiconductors, doping semiconductors can kill the conductivity, which results in the pin junction and also other semiconductor devices. In quantum dots, doping enabled the possibility to further tilt the emissions of quantum dots. For example, if we can dope manganese into zinc selenide, then you achieve yellow emission. If we can dope copper ions into zinc selenide, we achieve green emission. And there are different fabrication strategies, including nucleation doping and also growth doping. For nucleation doping, so the dopant was mixed with the precursors, and after the formation occur, then you can further growth a small shell. And for growth doping, then the dopant was mixed with during the growth process. So except for size, composition, and the doping, so the fabrication of quantum dots also enable the structure control. This is quite different with the conventional semiconductors. For conventional semiconductors, the only successful is to fabricate multi-layer superlattice structures, but it's quite challenging because of the lattice mismatch induced the strain effects. However, these effects can be overcome in small-sized quantum dots. For example, we can fabricate type 2 core shells and multi-layer core shells for white light generation, and also the heat junctions of nanorod. So I just briefly describe the fabrication of quantum dots. Now I will shift to the applications. So from the viewpoint or applications, I would like to firstly mention the Bell applications, because these Bell applications contains very smart chemistry for the surface modification. So in the hot injection, the obtained quantum dots can be only dissolved in non-polar organic solvents. So by changing the organic ligands into a bifunctional cell carbonic ligands, and we can fabricate quantum dots well dissolved in water. And there are also different ways by silicon encapsulation. And this strategy enables the phase transfer of QDs from organic phase into aqueous solutions. And if you want to learn the details, the paper can be referred to this 2 science paper. And this enables the exploration of quantum dots in different bioimaging systems, except for bioimaging. So the solution process, the quantum dots occurs in aqueous solution also have a lot of opportunities to be functionalized by DNA, peptides, aptamers, proteins, antibodies. For with these biomolecules, and they can be applied for multiple biosensing, such as like immunoassays, living cells, imagings, and others. So here I just list a simple shape. For example, by combining quantum dots with the organic dyes on the surface, we can employ the fry between quantum dots with and the organic dyes for bioanalysis. So QDs can be good light absorbers to be applied in photovoltaics because of the tunable absorption ability. They can be applied as colloidal dyes for dye synthesis solar cells, and also they can be absorbers layers for thin film solar cells. Except that they can be also embedded into organic polymers for hybrid polymer solar cells. So here I list 2 representative works, and one is from Professor Sargent, and they reported the efficiency PV devices with efficiency approach to 12% in 2016. And with the aid of perovskite quantum dots, the efficiency now approach to 6.6 for the hybrid system from quantum dots. Okay, now we have shift to the light-emitting diodes. I think many of you may be familiar with that because of the PN junction of light-emitting diodes have been very successful in generating white lights, and the efficiency is quite high, in particular for gallium nitride, and which was invented in 1990s, and they become the popular light source for lighting, general lighting, and also for display for others. So, however, for blue light, the efficiency is quite high. Well, there is a gap between them. For green light, inorganic light-emitting diodes, the efficiency is only 10%, which is lack of the counterparts of blue and red ones. So for white lighting, they need RGB colors. So they use another way to generate the white lighting. For example, so they can utilize blue LED gallium nitride chip with phosphorus and to generate white light. So the incorporation of quantum dots can improve the color quality by increasing the color rendering index for general lighting, or expand the color gamut for displays. Currently, there are two ways to achieve QD lightings. Firstly, quantum dots can be applied to replace conventional inorganic phosphorus for generating phosphor converted white LED. And this kind of white light generation was first reported by Professor Demer in 2007. And he firstly applied cadmium selenide quantum dots for white light generation. Well, the performance is very poor because of the stability issues. So in the past few years, we have been involved in developing low-cost, like copper indium sulfide quantum dots for general lighting. With that, we can achieve CRI value of 95%, which means with aid of quantum dots, we are able to generate very similar white light with the sun. This is the one diamond that we achieved before. So lasering is another interesting directions. And the QD laser was first reported by Professor Victor Klimov in 2000, and he obtained the stimulated emissions in cadmium selenide quantum dots. And after more than 20 years development, and they are recently, I think there are different reports on the continuous wave pump the laser. And this is quite important because with that, this means it's possible to generate lasering, in particular for electro field pumping lasering with quantum dots. So finally, I would like to mention the QD for compact spectrometer. Everyone uses cell phones. In our cell phones, there is an important factors is the camera, and this camera only gives light of green, red, and blue color, and also with intensities. So if we can achieve the spectrum with this camera, then it's easy for us to enhance the identification of materials. So this compact spectrometer is very important and interesting directions. And Professor Bawendi, working with Professor Jie Bao, and they reported the use of quantum dots as tunable color filters for this compact spectrometer in 2015. So here I have a summary of the QD related publications, and even that there has been a long time, and QD is still an interesting topic, and receiving increased the attentions. And each year there are like 10,000 papers was published right now, and there are still many important ones, which was published in Nature of Science, means that this the topic of QD is still very interesting and received a lot of attentions. So my group have been working on perovskite QDs in the past 5 years. And we focus on the in-situ fabrication of PQDs. And we explore the display and sensor applications. And we also involved the part of the commercialization of perovskite QDs. So now I will shift to the key point of my second part, in-situ fabrication of perovskite quantum dots. So as I mentioned, the use of QD improved the color quality of white lighting or display. And for display, there are different technologies. So LCD is the most popular technology in the market. And OLEDs, they appeared in the market of cell phone. Mini LED, they are successful demos. QD display, they are successful demos. So in all the applications, QD are quite important. So they are first TVs from Sony and successfully from TCL, and demos of QLED from BOE and Samsung. And there are also QD-based LED lamps. So although great success have been made in the past few years, there is still a gap between the fundamental science and the industrial requirements. So the key point is the fabrication of QD for display application experienced very long processes. So the key issues is the high cost due to the complicated processes. For example, for LCD backlights application, and we start from precursors, then the precursors experience the high temperature reactions at about 300 degrees. These preformed QDs were purified and as a QD solution, and they were further incorporated with the polymer and fabricated into thin films through roll-to-roll processing. So for display, there are now 3 choices. Cadmium selenide, which is a very popular materials and had been explored for more than 30 years. Indium phosphide, and they have been studied they have been explored since 2002, and the perovskites and very nearly materials. Compared with cadmium selenide and indium phosphide, perovskites show easy processing ability. So here I would like to briefly introduce perovskites. So Halide perovskites is the typical materials, and the key difference is that they are ionic compounds with a formula of ABX3. That A can be methanol ammonium and or cesium, and B can be lead or tin, and X can be chloride, bromide, or iodine. So by varying the highlights, the perovskites cover the whole range of the visible region. Halide perovskites have been well known for about 100 years, but they just enter into the field of semiconductor industrial only in the recent 10 to 12 years. So in 2009, perovskites was first incorporated into dye-sensitive solar cells, and with just 12 years, the highest efficiency exceeded to 25%. Perovskites have been very successful in developing as a gain medium for lasers, sensor sensitive materials for sensors, and the materials for high energy detection. So the exploration of perovskites as light emitters was originally investigated in 2004. However, the EL device can be only worked at very low temperature, such as 77 Kelvin. So when people revisit it in 2014, the problems are still here. The perovskite-based device, they show very low PR efficiency at low excitation powers and a low EL efficiency at low current density. These phenomena have been explained to the existence of sub-bond defect states. So how to overcome the recombination through trap defects? If that, then we have potential to achieve high photoluminescence. Actually, the principle is quite simple, because the success of quantumers tell us if we can reduce the size of semiconductors, we have potential to achieve enhanced PR properties. Firstly, with the size decrease, the number of the intrinsic trap defects will be greatly reduced due to the volume shrinking, and may be further reduced due to the auto-excluding effects. While the X bonding energy will increase with the size decrease, and which enable the fast recombination of the axon. However, with the size decrease, the surface effects will be more pronounced due to the increased surface to volume ratio and increased surface entropy. If we can prepare perovskite nanoparticles with well-kept surface, then it's possible to obtain enhanced PR properties. So the LARP synthesis was developed based on the solubility difference of perovskite precursors in different solvents. We firstly determined the solubility of perovskite precursors in different solvents. Firstly, and as we showed that perovskites can be well dissolved in polar solvents, but non-soluble in non-polar solvents. And we just choose two pairs for the fabrication. Toluene and DMF, they are miscible ones. And hexane and DMF, they are immiscible pairs. So the fabrication is quite simple as follows. Firstly, the precursor was dissolved in DMF and they were dropped into toluene. Without ligands, we obtained micro-sized particles and they are non-luminescent. With the aid of octanoamine and oleic acids as co-ligands, we obtain like small-sized Claudio solutions with average size of 3.3 nanometers. And by varying the highlights, we can tell the emission color from blue to red. So we found that even that in glove box, the red iodide-based perovskite quantum loss experienced a very fast degradation. We then spent time to investigate the degradation of iodide perovskites. So here is the conclusion. If we use DMSO, DMF, and THF as polar solvents, they are coordinated solvents. So the resulting perovskite nanocrystals have residue solvents molecule on the surface, and they are easily be exchanged with moisture, and they are degraded, even that in glove box. Well, the samples obtained using GBL or acetonitrile, they are non-coordinate solvents. So the resulting crystals are purified, are ideal crystals, and they can be stable in the open air even for more than 3 months. With that, we can tell the size, average size from 6.6 nanometers to 30.3 nanometers. So we also spend time to investigate the surface properties, because for most of the QDs, surface determines the PR properties, and the results shows that the system for QDs, they show broadly rich the surface, and also we investigated the temperature dependent PR. Interestingly, perovskite conductors can show very high PR intensity even at high temperature of 120 degrees. So we also explored the incorporation of this PeLED into polymer films, and we demonstrated the first LED devices with the white color gamut by combining green perovskite QDs with KSF as a red phosphorus. So after that, so we want to explore the use of perovskite QDs for display applications. For that, we need to purify them from a solution and process them into thin films or polymer composite films. So the challenge is how to find a suitable pair of polar and non-polar solvents for isolation and purification, because perovskites can be easily dissolved by polar solvents. So here we just developed a modified LARP synthesis, denoted as Emulsion LARP synthesis, by using DMF and hexane as emissive pairs. By introducing oleic acid as co-ligands, so we obtained an Emulsion solution. By using acetone or acetone nitrile as the Emulsion, we obtained a good colloidal solution of perovskite conductors. And with this, we can centrifuge and obtain the perovskite conductors as a powder. And these powders, the size can be varied by controlling the process. And also, by keeping the solution for a few days, we obtained perovskite nanoplatelets. And you see that it's quite uniform. And this method is also versatile for fabrication or inorganic silicon lead bromide QDs. And here are the samples. So the resulting perovskite powders obtained from Emulsion LARP synthesis was sent to UCLA. And we collaborated with Professor Qibing Pei, and we demonstrated the ER device. So although it's like the earlier devices are not quite good, but they show EQE of 3% with a brightness of 6,000 CD per square meter. And it's quite promising as earlier devices. And Professor Qibing Pei, they have very good technology for flexible electrode. And by combined with silver nanowires covered polymer electrodes, and we further achieve flexible devices. You see that the performance, the brightness, and the accuracy are comparable with these devices on ITO glasses. So although perovskites show very promising as emitters or ER devices, at that time we tried to compare with perovskite conductors with conventional cadmium selenide or indium phosphide QDs. So what advantages? Why perovskite QDs? So here I would like to share the standout advantage of in-situ fabrications, and this is also the key point of my talk. And here that I would like to first introduce the in-situ fabrication. For conventional QDs, as I mentioned before, they start from precursors and they experience the nucleation and growth at high temperature to form QD solutions. Then the QD was purified as high concentrated solution, they were further processed into thin films or incorporated into polymer composites for applications. And here, for perovskites, they can start from the precursors, and they can directly form thin films and through in-situ fabrication. So as I mentioned, that when quantum dots was firstly developed in Soviet Union, and they investigate the quantum dots embedded glasses, and actually this in-situ fabricated perovskite quantum dots in polymer films, they bridged the QD in glasses with QD in solutions. Here I have 3 stories, and the first is about the in-situ fabrication or perovskite quantum dots for electroluminescence application. So as we all know that the OLED is already on the way of commercialization, and the QLED, the performance of QLED also comparable with that of OLEDs. How perovskite QDs can be success? I think here the only opportunity is the in-situ fabrication through direct coating of the precursor solution, because this avoid the high temperature synthesis of QDs. And also the expensive equipment for vacuum of OLEDs. However, the challenge of in-situ fabrication or PeLEDs is how to obtain thin films of perovskites. In the regular way, perovskite films that obtained from a spin coating of perovskite precursor solution are rough and non-uniform with large grain size. In 2015, Professor Tao Li from Korea, he developed a nanocrystal pinning strategy by washing out the good solvents with anti-solvent. And he reduced the size into 100 nanometers. And he achieved a current efficiency of 40 CD per amp with an EQE of 8.53%. This is a very interesting result, and inspired other investigations. Professor Barry Round from Princeton and Professor Haizheng Jin from Jena University, they reported the further improvement by reducing the grain size into less than 10 nanometers. So we inspired by this progress, and we have tried to think about what happened during the adding of anti-solvent during the spin coating. Here I have a short movie to show the process. So as you've seen, that we observed a color change during the spin coating at the 7th seconds. So with that, then we have tried to understand what happened during this color change. Here I have a scheme for that. So after dropping the precursors with the spinning, a liquid precursor film was first formed. Then with the evaporation of solvents, perovskites start to nucleate and grows. By adding the anti-solvents, the growth was stopped. So here is the mechanism for this nanocrystal pinning. With this understanding, we just changed this process, and by adding the anti-solvent before the color change, with that means the good solvent and the bad solvent, they mix on the chip And this method was denoted as in-situ on-chip LARP fabrication. This is very similar to what we did in the flask. Good solvent and bad solvent, they mixed on the chip. And with that, I have a short movie to show you how it works. So we add unsolvent at the 5 seconds. So we see that after adding the unsolvents, before the color change, a very brightly luminescent thin films can be fabricated. So here here in the left of the figure is summarized the results. For the samples obtained from NCP, they show 20% of the quantum yield, which is similar with Professor Tongwuli's report. While the samples obtained from in-situ on-chip labs, they have a pure quantum yield about 8%. And with that, then we also did the TM measurements. The results shows in the right picture, and the resulting samples they have average size of 10 to 20 nanometers, and the surface is very uniform. And this enables us to fabricate the high efficient devices with a maximum EQE of 16.3% for the green perovskite QDs. Actually, this method is quite universal, and we have also tried to explore the fabrication of light-emitting devices, and we explored the use of different power solvents such as DBL, DMF, and DMSO, and we found that the power solvents controls the nucleation, and the color change point is different. For DMF, it's the color change occurs at the 5th second. For DBL, it occurs at the 10th second, while for DMSO, it occurs at the 70th second. And this helps us to control the in-situ on-chip fabrication. And with that, we also achieved efficiency devices of right color in 700 nanometers with a maximum EQE of 15.8%. So compare with the devices in green and near infrared. So the devices, the perovskite electroluminescence devices in the blue region lags off. And here, the efficiency is quite poor. And very recently, we also developed the in-situ fabrication of organic perovskite nanocrystals in blue region. And here is the paper, and I just tell you the case study. And we use the PEA bromine as ligands because it can control the formation of low dimensional quartz 2D perovskites. While DPPA, they have a larger size and they control the formation of three-dimensional perovskites. By mixing them together, we can control the quantum value distribution from small n value to the large n values. And here are the results. So by optimize the ratio between PA bromine with the DPPA, and we can optimize the blue emitter of perovskites, and we achieved a high PR quantum yield, about 16%. And we also explored the transient absorption spectra. And here I don't have time to explain how we analyze them, but the explanation is here. We can tells the quantum value distribution. The samples with PEA show very broad quantum value distribution with central at 3. While the sample obtained from DPPA, they show large n values with n value from 3 to 5. By mixing them, we can control the quantum value distribution, and we can narrow down them and mode the central of the n values to n over 4. And this narrow down enable efficient energy transfer from a high n value to low n value, and also suppress the back transfer from n over 4 to n over 3. And this enable us to fabricate efficiency and stable blue emitting EL devices. And we achieved peaked EQE about 8.8% with an average of 6.4% with good maximum luminescence. So now I would like to shift to another story. It's about QD-based LCD display backlights. So LCD is the most popular product for display applications. For the color quality was determined mainly by the backlights. So there are different ways to incorporate backlights into this LCD, such as the QD in glasses tubes, QD on chips. But the most successful way is the QD enhanced films. So this was firstly developed by Nanosys and 3M, and for conventional cadmium cylinder or indium phosphide, they experience a long process for the fabrication, and they need very thin films, thin barrier films to cap them. Well, based on the solubility of perovskites, we invented the in-situ fabrication or perovskite conducts inner the polymer matrix. So the process is quite simple. Firstly, a mixed solution or perovskite precursors with polymer or PVDF, and they were cast onto a substrate. With the evaporation of solvents, we obtain a transparent thin films, and they show very high photoluminescence under UV light. So the key point is control the drying under vacuum pumping. And by varying the highlights, we achieve the tunable emissions from blue to near infrared. And all of them show very high photoluminescence quantities. And by combining the green thin films with KSF as the red phosphorus, we achieved LED diamonds with color gamut of 120 NTSC with luminescence efficiency of 109 lumen per watt. And this is much better than the conventional phosphor-based LEDs. And with the development of Zhong Nanotech and Hefei Lucky, and they developed the scale-up fabrication with a width of 1.5 meters. And here is a LCD diamond or computer screen. Yeah, here is the MacBook, and here's the QD display screen. Yeah, and both of the brightness and the colors greatly improved. And working with TCL, and we demonstrated the first TV demos in 2008 in CES shown, and also the SID shown. And after 2 years working, and we also solved the stability issues. So currently the thin films can pass the test of the accelerated high temperature and high moisture test. So in the last year, TCL start to publish the products of perovskite QD embedded TVs. The first batch, they sell the first batch of 500 TVs in the last November, and it's predicted to have a large amount of TVs in the market. In addition to the hybrid perovskites, and we also employed the fabrication of all-inorganic PQDs. Here are the example of silicon lead iodides, because for display applications, we also need emissive PQD films with central emitter at 630 or 640. By tuning the solubility of the precursors, and we achieved the RB doped silicon lead iodide QDs, and with central emitter at 625. And here are the resulting samples, and by combining both of the red and green composite films, and we achieved a very efficient white color gamut LCD backlight demos. Except for the solution process, there are also ways to explore the fabrication of polymer composite films with perovskite QDs by the polymer excretion process. This process avoids to use the organic solvents by mixing PMMA with perovskite precursors. Then the precursors was milled and heated at high temperature, and this gives you also very good transparent, high and highly luminescent composite films. Considering the backlights, except for the color gamut, there are also challenges to improve the energy efficiency by using polarized composite films, because the power laser in LCD backlights greatly reduce the light efficiency. By combining the stretching with during the in-situ fabrication process, and we obtained PQD composite films with polarized emitter, with polarized emissions, and the polarization degree approached to 0.3. And also, the process can be further applied by adapting the electrospinning fabrication, and this also gives you perovskite nanocrystals with the rod shape inner the polymer nanofibers. So here I would like to show you about the patterning technology. For LCD, we need a bulk films, but for micro LED or OLEDs or QLEDs, we need a patterned quantum dots converters. And usually that there are two ways. One is that to use the OLEDs as blue lights, and also if we can use QD with green and red colors as the two pixels, then it's possible to reduce the cost of the fabrication, and also enable the uniform display qualities. So by just printing the perovskite precursors onto the polymers thin films, and we developed in-situ printing fabrication or patent PeLEDs. And this method is quite simple. So we fabricate perovskite QD's patterns by printing perovskite precursor solution onto a preformed polymer thin films. With the drying, PeLEDs was in-situ formed as a patent. So recently, we further demonstrate another way by using laser as a light source. And this also enables good patterns. And the most attractive things is that we can achieve very small size, less than 1 milliliter, 1 micrometer. So I showed you that the use of this PeLED for display application, either as a color converters for LCD or as a patent PICOs for micro LED or OLEDs. And here I want to show other applications. For example, PeLED thin films, they show high PR quantum mode with high transparency, and they can be very good light converters to enhance the silicon devices or silicon photodetectors after coating the PeLED thin films. They show enhanced responsibility in the UV region. And this also works for solar cells by coating the silicon solar cells with perovskite QD thin films. And we can also obtain 1%, nearly 1% enhancement for commercialized silicon solar cells. And there are another way to apply PeLED in miniaturized spectrometer, and by using non-emissive perovskite QD as color filters, and we can demonstrate a CCD spectrometer with high resolution approach to 2 nanometers. And this is almost approach to the human villain. So I just showed you how perovskite QDs can be fabricated in the polymer matrix. Actually, they can also in-situ fabricate in the single crystals. And this is a well-known example of system lead bromide 1,3 QDs embedded 4,6 single crystals. I don't have time to show the details, but I would like to show you the in-situ fabrication in the single crystals of perovskites. Also gives very interesting opportunities to explore the opticals of perovskites. Okay, I think this is all of my talk, and it's a quite long one. And I just talk about the in-situ fabricated perovskite nanocrystals. I believe it provides a revolutionized methodology to fabricate optical materials for photonics and optoelectronic applications. And this in-situ fabricated perovskite quantum dots bridge the use of quantum dots in photonics and optoelectronic applications. We have shown that how they can be applied in LCD backlights and also for electroluminescence applications. And there are different ways to achieve photo detectors, solar cells, and piezoelectronics. And here I borrow one sentence from Feynman, and there's a plenary room at the bottom, but better to be low cost. Here, finally, I would like to thank my collaborators and my students and my funding support. And without them, we can't finish these works.